Welcome to the deep dive. Today we're plunging into a really persistent challenge in neural networks, just how sensitive they are.
Right. Extremely sensitive.
Yeah, I mean, you can have a perfectly trained AI, classifies images great, but then you make this tiny, almost invisible change to the input.
A few pixels off.
Exactly, and bam, the network gets it completely wrong. We call those adversarial examples.
And they really show a core vulnerability, don't they?
They do. And it's not just that. This same sensitivity causes headaches during training, too. Instability, where learning just goes off the rails.
Or overfitting.
Yeah.
Gets too good at the training data, but then fails on anything new.
So researchers have been trying for ages to make these networks more, well, robust or stable.
Mm-hmm. And one really powerful mathematical tool for this is enforcing something called Lipschitz bounds.
Okay, Lipschitz bounds. What does that mean in practice?
Conceptually, it's like setting a hard mathematical limit on how much the network's output can change when the input changes.
Ah, so it guarantees a more predictable, stable response. Stops those wild swings we mentioned.
Sort of like a strict speed limit for how fast the output can react to input shifts. Keeps things controlled.
Got it. And our mission in this deep dive is to explore some really groundbreaking research that tackles this, specifically for large language models, for transformers.
Because extending this idea to complex things like transformers, well, that's been a big hurdle.
Right. It's not just about applying the bounds once. The real trick, apparently, is maintaining them, keeping them enforced through the whole training process.
That's the challenge. Yeah.
So we're asking, can these transformers with small enforced Lipschitz bounds actually perform well? And, how do different ways of constraining their weights affect that trade-off between performance and stability?
Yeah, and to really get why that's tough, we need to talk about the instability you often see when training these huge transformers.
Okay.
Researchers see these internal values, especially in the attention mechanisms and the final output logits, they can just grow enormously, explode, really.
And when that happens,
You get these dramatic loss spikes. The model's error rate suddenly shoots up, and sometimes the whole training process just diverges, stops learning.
right, and people usually use things like layer normalization or QK normalization.
Or logit, softcapping, yeah. Those are common fixes.
But the feeling is they're more like bandages.
That's how some researchers see them, yeah. Bandage fixes. They help stabilize training, sure, by reining in those big values, but they don't really fix the underlying sensitivity. No fundamental guarantees.
So this new research wanted to see if enforcing Lipschitz bounds could be a more foundational solution, get past just patching symptoms.
Exactly. Could it provide that core stability?
And this is where the main innovation seems to be, because attempts before, like Lipsformer you mentioned,
Right, Lipschitz.
they didn't actually constrain the weight matrices during training.
No, and that's the crucial part. If the weights can drift around unpredictably while learning, you lose those stability guarantees you're aiming for.
So what's new here?
This research introduces new tools, computationally efficient ones, specifically designed to maintain these norm-constrained weight matrices throughout the entire training run.
Ah, okay. So the bounds are enforced constantly.
That's the breakthrough. It finally lets people train transformers where these Lipschitz bounds are truly enforced, start to finish.
Like building stability into the structure itself, not just adding it on later.
Precisely.
Now, one of the really fascinating things you said was kind of unexpected. The optimizer.
Yes. The choice of optimizer turned out to have a huge impact on that trade-off between the Lipschitz bound and performance.
How so?
Well, they compared AdamW, which is, super common, very widely used.
The standard, almost.
Pretty much. They compared it with a less common one called Muon. And the results were interesting. Standard techniques like weight decay or spectral normalization. They gave much better results, so similar performance, but with a lower Lipschitz bound when the models were trained using Muon.
Muon. Why would that be? What's special about Muon?
It has this inherent property. When Muon updates the model's weights, the updates themselves naturally have a small, known spectral norm.
Spectral norm. That's like a measure of how much a layer can amplify the data.
Loosely speaking, yes. A small spectral norm for the updates means Muon is intrinsically quite gentle in how it changes the weights. It doesn't suddenly push them way out, which could break the Lipschitz bound or cause instability.
So it naturally works well with trying to keep things constrained.
Exactly. It's a really good fit for enforcing these strict Lipschitz bounds, leads to more controlled, stable learning.
Okay, so building on that, especially with Muon, They came up with new ways to enforce these weight constraints.
Two novel methods, yes. The first is called spectral softcapping.
What does it do?
It efficiently clips or limits the singular values of the weight matrices if they go above a certain threshold.
Singular values. So like the strength in different directions within the matrix.
That's a good way to think about it. Spectral softcap smoothly puts a lid on how much any part of the weight matrix can amplify things. And crucially, there's a theorem in the paper that proves it can reliably bound the weight norm when you use it with Muon.
So it guarantees the constraint is maintained during training with Muon.
Correct. That directly addresses that core challenge.
But Muon isn't always the optimizer people use. What about AdamW?
Right. So they developed a second technique called spectral hammer. This one is maybe better suited for AdamW, where Muon's special property doesn't apply.
Spectral hammer. Sounds direct.
The description is kind of like a hammer that strikes the nail that sticks out the most. It finds the single largest singular value in the weight matrix, that's the nail sticking out, the direction with the most amplification potential, and it just sets that value down to a desired maximum.
So it targets the biggest potential problem directly.
Exactly. It's a practical way to control things with AdamW, but it's worth noting it doesn't come with the same formal proof about maintaining the norm constraint, quite like spectral softcap does with Muon.
Okay, a different approach for a different optimizer. So did it work? Could they actually train transformers this way?
Yes, they successfully demonstrated it's feasible. They trained transformers up to 145 million parameters using these methods.
That's getting towards a reasonable size.
Definitely. It shows these aren't just toy examples. They got, for instance, a transformer with a Lipschitz bound less than 2 to achieve 60% validation accuracy on Shakespeare text.
Okay.
And a 145 million parameter model on internet text with a bound under 10 got 21% accuracy. So the constrained models can learn and perform reasonably well.
But how did they compare to, say, an unconstrained model? Like NanoGPT?
That's where the trade-off becomes really stark, maybe even a bit bewildering. To match the NanoGPT baseline validation accuracy, which was 39.4%, the Lipschitz upper bound for their constrained transformer had to increase to an astronomical number.
10 to the power of 264.
10 to the 264, that's huge, almost meaningless.
It's staggering. And it really highlights this tension. It suggests that maybe our current mathematical tools for calculating these global bounds are giving us worst-case scenarios that are incredibly loose, way overstating the network's typical amplification.
So the theoretical bound is massive, but maybe the network doesn't actually behave that wildly in practice.
That seems to be the implication. It really raises questions about whether chasing a perfectly tight global bound is the right goal, especially if you need top performance.
But one really big win, you mentioned, was stability without the bandages.
Yes. This was a key finding. These Lipschitz-constrained transformers, they train stably without needing things like layer norm, QK norm, or logit softcapping.
Those things they took out of the NanoGPT baseline for comparison.
Right. And when they took those out of the standard NanoGPT without adding the Lipschitz constraints, that baseline model just diverged. Training failed completely. Wow. So that directly supports the idea that enforcing the Lipschitz bounds is providing a more fundamental stability.
It really suggests a path towards intrinsically stable architectures, moving beyond those post-hoc fixes.
And that connects to another kind of paradox they found, right, about the activations.
Exactly. Despite calculating these incredibly high theoretical Lipschitz bounds, like that 10264 number, empirically, when they actually looked inside the models during training, the maximum activation values were surprisingly small.
How small?
For that same model with the huge theoretical bound, the largest activation value they saw was only about 160.
Okay,
Compared to the unconstrained baseline, which saw maximum activations hitting nearly 150,000.
Whoa, okay, big difference. 160 versus 148,000.
Massive difference. So again, it suggests the global bounds are mathematically correct for the absolute worst case, but maybe very loose approximations of typical behavior.
And that could be really important, right? Small activation values.
It's potentially very promising. Empirically small activations could open up huge possibilities for using lower precision numbers during training and inference, make the models much more efficient.
Less computationally demanding. Okay, that makes sense. And did the research also confirm the link between lower Lipschitz bounds and robustness?
It did, yes. They confirmed prior findings there. They showed a nice example with two simple MLPs, multi-layer perceptrons. Both had similar accuracy on clean data, but one, trained with Muon and spectral softcap, had a really low Lipschitz bound about 15.
Okay.
The other, trained with AdamW and standard weight decay, had a much higher bound, over 7 to 600.
Big difference again.
And when they hit both models with adversarial perturbations, those tiny input tweaks,
Yeah.
the one with the low Lipschitz bound, the 15, kept much, much higher accuracy as the perturbations got stronger,
So this is far more resilient.
directly showing how that tighter bound translates to better robustness against attacks. A real practical benefit for security and reliability.
Now, to actually make all this work in a transformer, they had to change the architecture itself, not just add the weight constraints.
That's right. Several key adaptations were needed. It wasn't just about the weights. For example, the residual connections.
How did they change those?
They reparameterized them using what's called a convex combination. This is important because standard residual connections can let the Lipschitz bound grow exponentially with depth, which becomes unmanageable fast.
Ah, so the convex combination helps keep that growth under control.
Exactly. It helps ensure the overall bound stays manageable as you stack more layers. And another change was in self-attention.
What did they do there?
They used a 1 over d scaling factor instead of the usual 1 over square root of det.
Seems like a small change. Why?
It's essential for guaranteeing Lipschitz continuity within the attention mechanism itself. The standard scaling doesn't provide that mathematical guarantee.
Got it. So you bound things within each layer, control the connections, and then combine it all.
Pretty much. You bound the activation norms layer by layer using these modified structures and weight constraints, and then you compose those layer-wise bounds to get a global Lipschitz bound for the whole transformer.
Okay, so let's wrap this up. The core achievement here seems to be a practical method for training transformers with these Lipschitz bounds enforced the whole time.
Yes, a really significant step forward for making these powerful models more intrinsically stable and robust, tackling those long-standing training issues.
When crucially, doing it without needing many of the usual stability tricks like layer norm or QK norm.
Right, which suggests it's addressing a more fundamental aspect of the model's behavior, not just papering over cracks.
And we also saw that really intriguing disconnect, the empirically small activations, even when the theoretical bounds were enormous.
Yeah, that phenomenon is fascinating. It might point towards new ways to think about or measure network stability beyond just those worst-case global bounds.
So this deep dive has definitely shown us some new, promising paths towards building more stable and robust transformers.
It certainly has, and it naturally leads you to wonder what comes next. What other architectural ideas or maybe completely new insights will we need to keep those Lipschitz bounds truly small as models get even bigger and deeper?
That's a great question. And maybe for the people really pushing the limits of scale, could this Lipschitz-enforced training actually end up being faster or more resource efficient or just more reliably stable than our current methods when we get to truly massive models? That remains a key question.